Crikey, look at this problem!
Of mass m, a centroidal radius of gyration, an outer radius, and an inner radius. Okay, that's in the picture here. We have a constant force that's applied to the smaller radius by an angle of theta that changes over time. The spool rolls without slipping on the rough horizontal surface. So now we need to determine the angular velocity in terms of theta. So for this problem, this is example 5A, so that means we're going to have to follow the steps that are given for 5A, which has a total of 7 steps. So our first step, like always, is to draw the free body diagram. So here we have a basic circle with a circle inside. We have two forces. We have the weight force coming from the center of mass going straight down, and we have the F, which changes over time, but we just drew it according to the picture. Step 2 is to define the coordinate system. We use the simple IJ Cartesian coordinate system because it makes life easy. Step 3 is to define all of our forces and write them in vector form. So we have two forces here. We have the weight force, which goes straight down like always, which is negative mg in the j hat direction. The force in the f direction is a constant force, and that's just equal to its force in the x plus its force in the y, I hat, j hat, respectively. Step 4 is to write the acceleration of each object in vector form. So we have an unknown acceleration, however, so we'll just write it as generically as possible. We have the acceleration through the point G is equal to the acceleration of G in the x plus the acceleration of G in the y, I hat, j hat, respectively. Step 5 is to combine steps 3 and 4 with Newton's second law, and so we get F equals ma at point G. So that basically is the sum of the forces equals m times ag total, which is what we have here, plus the weight force, or equals the weight force plus the force constant. Step 6 is to write this in scalar form. So we have two scalar equations now. We have fx equals magx, and then we have fy minus mg, which is our weight force from up here, and that equals the acceleration in the y direction.
Then we move on to step 7, which is the moment equations. So for this equation, we did our moment through point G because that would eliminate a moment from the weight force. So our equation gave us the sum of moments at point G equals Ig times alpha. And then when you plug in your equations earlier, you get Ig alpha equals Fxr plus Fyr, which is the moment being caused by the force. And we know from earlier that Ig is also equal to the mass times the radius of gyration, which is kg squared. So we plug that in, so you get mass times radius of gyration squared times alpha equals Fxr plus Fyr. Then alpha, when we divide by mass and the radius of gyration squared, we get alpha equals Fxr plus Fyr over mass times radius of gyration squared. And we know, based off the image above, that Fx is F cosine theta and Fy is F sine theta. So when you plug that in for Fx and Fy, you can factor out an F and an R. So you get cosine theta plus sine theta times Fr over mass times the radius of gyration squared. When simplifying this with the numbers given in the problem, we get a final alpha equals 3.2 times cosine theta plus sine theta in the k direction, and that's our angular acceleration of the spool as a function of